Hello class, today we will be covering measurements in chemistry. For the subtopics, we'll be covering what measurements are, and then we'll look at recording observations, and below that we have the subtopics of certainty and uncertainty, significant figures, and accuracy and precision. So to start, I looked up on Merriam-Webster what the definition of measure was, which when you look it up, it gives you first one about value, which is not what we're looking at, but the second one says the dimensions, capacity, or amount of something ascertained by measuring. Or when you click what measuring is, it tells you to measurement, which tells you the act or process of measuring, or also a figure, extent, or amount obtained by measuring. So you can bring all of that together and come to the definition that to measure something is to determine the amount of a quality or a specific thing, usually by comparing it to a standard. Let me repeat. To measure something is to determine an amount of a quality of a specific thing, usually by comparing it to a standard. So the important things is we are measuring something to determine an amount, a number, of a quality, something about a specific thing, usually using a device or comparing to a standard. So again, what does that mean? Well, it sounds kind of silly, but it can make sense if you think about some examples. So example 1. A person can use a measuring tape to determine that they are 1.625 meters tall as they are measuring their height. Right here, that's a 5'4" for any of you in the audience who this might apply to. So in this case, the person, a specific thing, is using a measuring tape, a standard, to determine that they are 1.656 meters, an amount, tall, which is their height, a quality. Example 2. A person can determine their pet's mass to be 7 kilograms using a home scale. So in this case, the specific thing is the pet. We're trying to figure out its mass, which is the quality. We know that it's 7 kilograms, which is an amount, and we obtained it using a home scale, which is a device. Lastly, we have a policeman catches you going at a speed of 88 miles per hour using his radar gun. In this case, the specific thing is you. What you're being measured is your speed, which we have an amount of 88 miles per hour, and the tool used for this was his radar gun. So the big thing of that is that to measure something is to determine an amount of a quality of a specific thing, usually by using a device or comparing to a standard. There's no way to measure something intrinsically. You can't just, oh, that's a foot long, or oh, that is 5 seconds. You can make a close approximation, but you yourself are not able to without the assistance of a device or a standard or a thing. So because we rely on devices or standards, we need to make sure that we record our measurements accurately. Why? Well, because measurements are a reflection of our reality. Every time you take a measurement, whether that person that was 5'4", that is how tall they are. That's how much physical space they take up in the Y direction in the real world. There is truth to that. So we need to be able to show the right number. The same way that I wouldn't say that that 5'4" person would be 5'6", I can't say that they're 5'4.5" unless my measurements actually tell me that. So as chemists, it is imperative that our data reflects the truth to the best of our abilities. When we report our numbers, we must be able to report what we know for sure versus what we don't know. But before we get into that, here's an example of what happens when you throw honesty out the window entirely. So you're probably not familiar with this face. This man is Jan Hendrik Schoen, who was a professor / researcher in the early 2000s. So he was a pioneer because he just kept coming up with all these crazy papers in semiconductors, in analytical chemistry, in electrical chemistry. All of his stuff seemed to be just the cream of the crop, and everyone said this guy was going to be the guy. He was going to change everything. He had findings in nature. He had things in science. He had all sorts of information and papers on a lot of journals, which a lot of people are lucky to get into once. He had multiple of them. And so why was this important? Because he faked all of it. So Jan Hendrik Schoen was found that his measurements did not match his findings. People started asking questions. He would shove them to the side, kind of delay them, depose them. So he'd be busy, you know. But eventually things caught up to him, and people found out that most of his data was fake. And the extent of how fake his data was so prevalent that Germany, his home country, stepped in and told his university to remove his PhD. This scandal led to people losing their jobs, not just the people in this image, but also the people that would be their support staff, you know, so like grad students, grad techs, lab techs, all of these people lost funding because they were working on a lie, essentially, right? And not just that, but it's a huge reputational hit, not just for him, but for the people that worked with him, right? All of these people should have been able to say, wait a minute, these don't make sense, he's lying, whatever, but nobody really cared enough to look through his measurements until it was too late. So I think this is a fascinating example of what can happen if you don't adequately keep track of your measurements. If you want to see more, I recommend you look on the YouTube channel Bobby Broccoli. He has a documentary on this exact case and is the source of this example. I thought it was so fascinating, I decided to add it here. So I recommend you go watch it if you have 2 to 3 hours of your time. Okay, so back to recording our observations. So how do scientists protect their work and report true numbers? Well, we need to understand the limits of our measuring tools and report our results to reflect what they tell us. What they tell us. We are trying to reflect the reality of the world, not what we want to do, which is what Hendrik Schoen was doing. So we also need to know what our numbers don't tell us. So to demonstrate an example, I will be summoning our friend Gary, who is a little goblin. This is Gary Gygax. He is our lab goblin. He is usually in the back working on stuff. So let's say that we decide that we are going to measure Gary, right? And we have this big ruler that measures in feet. We'll first put this little box behind him, which is the very bottom of his feet and the top of his head. That's how tall he is. And we put this ruler next to him, right? So we look here and we see that he is more than a foot tall, but less than 2. I could guess 1.7, 1.5, 1.6, but ultimately I know for sure that he has 1 foot of height and he does not have the rest of it. The rest of it I have to guess. So I guess I could make is 1.6 feet. I could say he's 1.6 feet tall. In that case, we have 2 numbers that are important. This first number is the one we are certain of this. We know for sure he is at least 1 foot tall. We know he is not 2 feet tall. So he's somewhere between 1 and 2. We are uncertain of this number. This 0.6 is higher than his half, but we don't know how much. I could have put 1.7. I could have put 1.5. The critical thing is I could not put 1.55, 1.65, 1.62. Putting a third number would be a lie because we for sure do not even know this one. Anything after that we would be making up. So we want to make this number as accurate as possible. It wouldn't make sense for me to say 1.6 if the line was down here, right? I would say like 1.2, 1.3. But here I am making a guess. And that's the important part that is important with measurements is at some level, at some point, we will need to make a guess and we need to understand what that guess is. So we do not report past this number because we are lying. If I said 1.62, that would be telling you that I am certain of the 1.6, which is not true. I'm only certain of the 1. Okay? So what if we get a better ruler, right? This one has little notches. I could now say 1.61 feet as his height is past the 1.6, but I don't know by how much. So in this case now, we are now certain of 2 numbers, the 1.6, and we are uncertain of the 1. Okay. When we need to report a measurement, we report everything we know plus 1 digit of uncertainty. So in this case, we did 1.61 because we knew the 1.6 because we can see 1.6, and we added that 1 to give one layer of uncertainty. There's a system for this. It's called significant figures, and it's the next topic. But before we do that, let's thank our friend Gary. Poof. Okay, so now that he's gone, let's talk about significant figures. Significant figures are the scientific way to report all of your numbers that are known and unknown so that other scientists can read your work and know what you have. So, for example, every measured number should have as many significant figures as the known and unknown numbers. From the Gary example, when he measured 1.6, we had one known and one unknown number. That means that we have two significant figures. When we measured him and he was 1.61 meters, not meters, feet, we had two known and one unknown, which is three significant figures. There are math rules to this that apply when you do multiplication, addition, division, but we will cover those another lecture. That said, we do read other people's significant figures, so we need to be able to learn the rules how to count so that we know when other people are writing what is real and what is not. Because of that, we do have rules, which in this case we have every number that isn't a zero is significant. Zeros between numbers are always significant. These are always known as middle zeros. Zeros that have no numbers before them are not significant. These are known as leading zeros. Zeros that end at a number may or may not be significant. We need more context. So these are known as trailing zeros. And trailing zeros are always significant if there is a decimal point anywhere in the number. These are a lot of rules, and I know that just memorizing them without example may not help. So we decided to do a couple examples, right? So in this case, we have a number, and we're going to report its significant figures. So we count. In this case, we say 5.13225. Every number that isn't a zero is significant. There are no zeros, so that's 1, 2, 3, 4, 5, 6 significant figures. Next up, we have this number, 5.1300002025. So in this case, zeros between numbers are significant. So in this case, there's a 3 and a 2 bounding all these zeros, so they are significant. There's a 2 and a 2 bounding this zero, and they are significant. It doesn't matter how many zeros you have. You could have 1 and then a million zeros and then another number, let's say 2, and all those would count because there's numbers bounding each side. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 significant figures. For this number, this is the same number as before, but now you can see it has a 0 to start. So zeros that have no numbers before them are not significant. So this 0 is not real. Essentially, we start at 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, which makes sense. It's the same number. And one thing that is important that I want to show you here is that these two numbers are written differently, but they have the exact same number of significant numbers. There is a reason for this, which is that this number and this number are multiplicative by 10. So you could report this, for example, as 5.13 decimeters and call this 0.513 meters. You would be able to convert them back and forth, and it would be the same number written differently. So to account for that, we want to make sure to count our significant figures so that we know. This way, if you divide the number by 1,000,000, 500,000, etc., you still have the same number and the same amount of significant figures. This one here, once again, numbers that have no zeros before them don't count. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 zeros, none of them count. We only count this 1, 2, 3, which is 3 significant figures. Next up, we have this one, which is 5132025. The big problem here is that we have 8 numbers, but there's a trailing 0, and there are no indications that there is any end here, a decimal, I should say. Because there's a decimal, there is not a decimal, we cannot say conclusively how many significant figures there are, because we could either have the 0 be significant or it could not be significant. If it was significant, it would be 1, 2, 3, 4, 5, 6, 7, 8. If it wasn't, it would be 7. But because we don't know for sure, we'll call it inconclusive. Last one, spoiler, 0.51320250. Trailing zeros are always significant if there is a decimal point anywhere in the number. You can see here that has 8 because it's 1, 2, 3, 4, 5, 6, 7, 8. And in this case, this decimal means that we do count it. Generally, this is important for the mathematics that we will do in another section. For now, I would like you as students to practice your significant figures so that you can get a better understanding of what's going on. Lastly, accuracy and precision. So these words are not interchangeable and they describe your measurements. So it's important that you know what you're talking about. There is a figure in your reading, which is here, that shows it relatively well. Other books use the same metaphor. When you're talking about precision, you're talking not about how accurate you are, but how close your measurements are. So in this case, you can see the archer got all of his bolts here, but he wanted to aim for this. So this measurement is precise, but it is not accurate. In this case, he is also accurate because he's hitting the right thing. There is another one, which is when he's neither, right? He's imprecise and inaccurate. There is another one, which is when you are imprecise and accurate, and that would just be a bunch of arrows that go in different places that average out to be in the center. But in this case, we will not be talking about that. So this has not much to do with significant figures when it comes to the process, but it does have to do in describing what your significant numbers tell you. So if you have a bunch of significant figures that are close to each other, you can say that they're precise. If your significant figures compared to the real value and they are similar, you can say that you are accurate. When you report out your numbers, you may be precise, but the goal is to try to get an accurate measurement. That doesn't mean make it up. That's what Henrik Schoen did. That just means do it right. Show things as they are, not as you think they should be. So for today's class, pretty short, we learned what a measurement is, and with that we're able to explain what info we are certain of and we are uncertain of, which we can then use significant figures to report. And lastly, we can determine whether we have accurate or precise measurements that way. Remember, your job as a scientist isn't to always be right, it's to be truthful on what you report, because you don't want to be known as a fraud. Thank you for another good class. See you at the next one.